We've all seen the incredible things large language models can do. They write, they code, they create art. I mean, it's genuinely astonishing.
It really is.
But, despite their power, they can often feel like these opaque black boxes.
Hmm.
You give them input, you get output. But understanding the intricate steps in between, that's the mystery, isn't it?
It absolutely is. On a global scale, these models are incredibly complex, highly nonlinear systems built on that transformer architecture, the one that really took off after that Vaswani paper.
Right? 2017.
Yeah. And seeing the amazing results is one thing, but actually getting down to the granular level, understanding exactly how a model arrives at a specific word prediction from a specific input sequence. Well, that's one of the big challenges in AI research right now.
And you, our listener, you sent us a really fascinating piece of research that dives directly into this challenge. It proposes a truly novel way, it seems, to gain insight into that black box.
It really is a standout academic contribution. It tackles this interpretability problem head on by identifying a, well, frankly, surprising property of these models,
Uh-huh.
and then it develops a powerful new method based on that very finding.
Okay, so for this deep dive, our mission is clear. Let's unpack the core innovative idea from this research.
Let's do it.
The paper argues that these big open-weight LLMs, despite their global complexity, show something called nearly exact local linearity for any given input.
That's the core claim.
And crucially, it introduces a new method using what they call the detached Jacobian to actually leverage this property for interpretation. So we're going to try and peel back the layers, understand these key technical innovations, and see what they reveal about how these models actually work under the hood.
Okay, but maybe first let's just quickly emphasize why understanding the how is so critical.
Good point.
I mean, beyond just pure scientific curiosity, which is obviously huge, knowing why a model says what it says is absolutely crucial for building trustworthy AI.
Right.
It's essential for safety, for spotting and maybe mitigating biases the model might have learned, and ultimately for figuring out how to make these systems even better.
Yeah, that makes total sense. We've talked about other interpretability methods before in these deep dives, things like sparse autoencoders looking for features or circuits inside the network.
Like the brick and paper described.
This research feels a bit different, though. It's maybe less about finding what the model represents statically and more about changing how we can mathematically analyze the computation itself for specific input. Is that fair?
That's a great way to put it. It's a shift in perspective, yeah. From finding fixed components to analyzing the dynamic operation for a given query.
Okay, let's zero in on that core innovative finding then. Local linearity. What's the paper's central thesis claiming here exactly?
So, based on their analysis of several open-weight models, they specifically mentioned testing Llama 3, Gemma 3, and Qwen 3. The paper's main argument is this. While these LLMs are definitely complex, globally nonlinear functions,
Uh-huh.
for any single input sequence you feed them, the mathematical operations they perform behave essentially as a nearly exact local linear system.
Nearly exact local linearity. That phrase itself sounds, well, almost contradictory when you think about a nonlinear black box. Can you help us visualize that? What does it mean in like simpler terms?
Okay, think of it like this. Imagine you're standing on a huge, incredibly wrinkled mountainous landscape, right? That landscape represents the model's overall global nonlinearity.
Got it. Very complex terrain.
Exactly. Now, if you zoom in really, really close on just the tiny patch of ground directly under your feet at one specific location, that location is your specific input sequence.
Okay.
Even though the whole landscape is rugged and bumpy, that tiny patch right beneath you, it appears almost perfectly flat. It behaves like a simple flat plane. That flat patch is the local linearity.
Ah, okay. I think I get it. So for that one specific set of words you put into the model, the incredibly complex calculations happening inside, across all those layers and components, they can be accurately represented as if they were just one big, straightforward linear equation acting on the input.
That's the core insight, yeah. And the significance of this from an academic and interpretability angle is massive.
Why so significant?
Because linear systems are, the bedrock of so much math and engineering. We have centuries of powerful tools, techniques from linear algebra, designed specifically to analyze linear relationships.
Right, like matrices, eigenvalues, all that stuff.
Exactly. So if we can accurately represent the LLM's forward pass locally as a linear system, we can suddenly bring all those sophisticated analytical tools to bear on it. That's what the paper means when it says this property offers a new path to interpreting a wide range of open-weight LLMs at a local level.
That makes a lot of sense. If you can turn a black box, even just locally, into something that acts like a transparent linear equation, you can analyze it in ways that were much, much harder before.
Precisely.
Okay, so that's what's the surprising property. Now the how. the novel method they developed to reveal this linearity, the detached Jacobian. Let's talk about that technical innovation.
Yeah, this is where the academic cleverness really comes in. The detached Jacobian is the key technical contribution here. Now, conceptually, a standard Jacobian in calculus is, well, it's a matrix of partial derivatives, right?
Uh-huh. It tells you how sensitive the output is to small input changes.
Exactly, at a specific point. And it's often used to find a linear approximation of a nonlinear function around that point.
Okay, so a standard Jacobian gives you a linear approximation near a point. How is the detached Jacobian different?
Good question. The detached Jacobian, as they define it in this paper, isn't just an approximation of the function nearby. It's a specific set of matrices derived from the LLM for a particular input sequence that exactly represents the model's forward operation as a linear system at that specific input.
Exactly represents it.
Yes. And critically, when you perform this linear operation using the detached Jacobian on the input embedding, you get the numerically identical output embedding that the original nonlinear LLM produced.
Whoa, okay, so it's not an approximation on the output, it's a different mathematical representation of the process that arrives at the exact same output, but structured linearly just for that one input point.
That's it?
And the Pable makes it clear this analysis method doesn't change the model's actual prediction, right?
Absolutely. The source explicitly states, quote, "The numerical output of the model remains unchanged." This method is purely an analytical tool. You perform it during inference to understand the computation path for the input that was just processed. It's not about altering the model's behavior, just gaining insight into it.
Fascinating. Okay, so how do they mathematically pull this off? How do they get this local linearity from a globally nonlinear transform? Where does the detaching part come in?
Right, this is the core technical move. They perform what they call gradient detach operations, strategically within the network during inference. Basically, they identify the specific computational steps inside a standard transformer that introduce nonlinearity for a given input,
Okay.
and then they cleverly modify how the gradient is calculated just for those specific steps. They effectively freeze or detach the nonlinear terms at the precise numerical value they happen to take for that specific input.
So they pinpoint the nonlinear culprits for that specific input and neutralize them for the gradient calculation. Which specific components are we talking about here?
The paper details three main areas where they apply this.
Okay.
One, normalization layers, things like RM is norm, which you find in many LLMs. These involve calculating the variance of the input vector and then dividing by it. That division step makes them nonlinear.
Right.
So to make them locally linear, they detach the gradient computation from that variance term. It's fixed at whatever numerical value it has for the current input. This is kind of similar to techniques used in other interpretability work, like freezing nonlinearities. For that one input, the normalization just acts like a simple scaling and shifting.
Makes sense. What's next?
2. Activation functions. Functions like SWIBLU, which is key in Llama 3, or GLU in Gemma 3, Swish in Qwen 3. These are nonlinear by definition.
Of course.
But many popular ones, including SWIGLU and Swish, can be written with terms involving simple multiplication, which is linear, and other terms involving nonlinear functions like sigmoid, or GOU's own complexity. The method detaches the gradient from the purely nonlinear part of the function, again evaluated at that specific input point. Effectively, only the linear component remains active for the gradient calculation.
Clever. And the third?
3. Attention blocks, specifically the softmax function. That's a key source of nonlinearity in attention, turning scores into probabilities.
Right, that normalization step.
Exactly. While the softmax output itself is nonlinear, the next step, multiplying by the value matrix, V, is linear. So the method detaches the gradient calculation from the softmax output itself, but crucially, it preserves the gradient contribution from the linear multiplication with V. This allows the whole attention block for that input to be represented linearly.
Okay, let me see if I've got this. By finding the parts of the standard transformer calculation that are nonlinear at the specific values they take for a given input sequence,
Mm-hmm.
they strategically perform these detachment operations in the gradient calculation. This doesn't change the final number crunching result, the output embedding,
Correct.
but it lets them mathematically represent that whole forward pass as if it were a single linear system captured by this special detached Jacobian matrix.
You've got it. The detached part of the name comes from this manipulation of the gradient computations. And by doing this across all the relevant components' attention, the MLPs with their detached activations, the normalization layers, the entire transformer decoder from input embeddings right to the final layer's output embeddings can be represented by this single composite detached Jacobian matrix. just for that specific input.
That sounds like a really significant technical achievement. How did the researchers actually prove that this detached Jacobian accurately captures the LLM's forward pass? Did they test it?
They did, empirically. It's quite direct, actually. They'd take an input sequence, run it through the original complex nonlinear LLM, and get the final output embedding vector.
Okay,
Then, for the same input sequence, they'd compute the corresponding detached Jacobian matrix.
right.
Finally, they'd perform the linear operation, multiply the input embeddings by this detached Jacobian.
And the result of that multiplication.
This is shown really compellingly in Figure 3 of the paper. The output vector predicted by the original complex LLM was nearly exactly reproduced by the simple linear multiplication using the detached Jacobian.
Nearly exactly. How near is nearly?
They quantify it, they provide a concrete measure. The relative error between the two output vectors was on the order of 10 to the minus 6 for calculations done with float 32 precision.
Wow, 10 to 6. For listeners who might not deal with floating point numbers daily, that's tiny, right? Especially with float 32.
It's incredibly small. Float 32 numbers themselves have a limited precision. An error on the order of 10 to 6 in that context is extremely close to the maximum possible numerical agreement you could even expect given the finite precision of the computer's math.
Okay.
So it provides really strong empirical validation that for a given input, the detached Jacobian isn't just some rough approximation. It is, within the limits of standard floating point math, a nearly exact linear representation of that nonlinear forward pass. And this is a key academic finding showing this property holds across the different open-weight LLMs they tested.
That level of numerical fidelity is genuinely striking. Okay, so now we have this powerful tool, this locally linear representation captured by the detached Jacobian. What kinds of insights can we actually extract by applying those linear algebra tools you mentioned earlier?
Right, this is where we start to really peer inside the local computation. One fundamental thing you could do is just examine the rows of the detached Jacobian matrix itself.
What do the individual rows tell us?
Okay, remember the detached Jacobian maps the input embedding space to the output embedding space. It essentially shows how changes in the input tokens influence the final layer's activations.
Uh-huh.
So each row of that Jacobian corresponds to a specific unit or dimension in the final layer's output embedding. By looking at the rows that have large magnitude norms, the ones with big values, we can see which input features, which input tokens, had the strongest influence or activated that specific output unit just for this particular input sequence.
And can you make sense of those rows?
Yes, because you can decode these rows back into the vocabulary space. When you do that, you often see which input words were most salient for that part of the output representation.
Ah, like in figure 4A of the paper, where they decode some of these influential rows, and you clearly see words from the input sequence popping out, like bridge, marin, and is.
Exactly that. It gives you a localized view of input saliency, which specific input words are driving the final representation for this specific sentence.
Okay, that's interesting. What about singular value decomposition, SVD? The paper discusses applying SVD to the detached Jacobian, mentioning it follows some previous work.
Right, SVD. It's a real workhorse technique in linear algebra for analyzing matrices. When you apply SVD to the detached Jacobian, they write it as J plus equals USVT. It decomposes the transformation into three key parts: sets of singular vectors, U and V, and corresponding singular values in the matrix.
Okay, what do those parts mean?
The singular values, the say card, tell you the strength or importance of different modes of the linear transformation. The singular vectors tell you about the directions in the input space, the V vectors, and the output space, the U vectors, associated with those modes.
And what did the researchers find when they looked at the singular values from the detached Jacobian?
This is another really key finding. They observed that the singular value spectrum of the detached Jacobian is extremely low rank.
Low rank, why is that significant?
Highly significant. It implies that while the LLM itself is massive and performs incredibly complex calculations overall, the effective dimensionality of a linear transformation it applies for any single specific input sequence is surprisingly low.
Huh.
Even though the full Jacobian matrix is technically large, the actual computation it represents can be accurately approximated by considering only a small number of the top singular vectors, the ones with the largest singular values. It suggests the specific calculation for one input might be, in a way, much simpler than the model's overall potential complexity implies.
So even though the model has billions of parameters, the actual computational path for one specific input sentence can be captured by a much lower dimensional linear process. Is that the idea?
That's what the whole rank strongly suggests, yes. And when you decode those singular vectors, you get even more insight.
How so?
The U vectors, when decoded back to the output token space, often correspond to plausible output tokens the model might be considering or is likely to predict next. Figures 4b and 5 show examples where these U vectors decode to words like most or one.
Okay. And the V vectors?
The V vectors, when decoded back to the input token space, often relate directly to the input tokens or the core concepts within that input sequence that are driving that specific computational mode. Again, in their examples, you see words like bridge and marin showing up.
So SVD essentially breaks down this localized linear computation into these core modes that seem to connect specific input concepts to potential output concepts for that instance.
Precisely. And you can take this analysis even further, layer by layer,
How does that work?
by computing the detached Jacobian not just for the final output, but for the output of each transformer layer individually. This lets you track how the linear transformation changes as the input signal propagates through the network.
Ah, right. This gets at that idea of semantic emergence, how meaning develops. The paper references tables 1, 2, and 3 for different models and figure 6. What did this layer by layer view reveal?
It revealed a really interesting kind of phase change or progression in how information is processed. In the earlier layers of the network, if you decode the singular vectors from that layer's Jacobian, they might seem quite abstract, maybe even like noise. Okay. But as you move into the deeper layers, the decodings start to become increasingly coherent and semantically relevant. Relevant both to the original input and to what the model is likely trying to predict.
Can you give an example?
Yeah, they show for an input sequence prompting the model towards Golden Gate Bridge that in early layers, the SVD modes related to bridge might be very generic. But in later layers, they evolve to include more specific terms like San Francisco or Golden, clearly building towards that final specific concept.
That's a really cool way to visualize how meaning is being refined and constructed layer by layer within the model's representation space, just for that one input.
Exactly.
What about dimensionality analysis? They mention using something called stable rank.
Yes, stable rank. It's a measure used to estimate the effective dimensionality of a matrix or transformation. It can sometimes be more informative than just the strict mathematical rank, especially when dealing with the inherent fuzziness of floating point numbers.
And what did analyzing the stable rank show?
Analyzing the stable rank of the cumulative detached Jacobian up to each layer, shown in Figure 6c, revealed a general trend. The effective dimensionality tends to decrease as information gets processed deeper into the network. This suggests some form of compression or focusing of information.
Interesting.
However, Figure 6d looks at the stable rank of each individual layer's transformation, not the cumulative one, and that shows more complex dynamics. They note things like potentially a large peak in dimensionality near the end of the network and decreases within individual attention and MLP modules deeper inside. It provides further, more nuanced insight into how the model utilizes its representational capacity layer by layer, again, specifically for that input.
So, okay, we get all these detailed academic insights, which input features matter for the output, how the computation breaks down into input-output modes via SVD, how meaning seems to emerge layer by layer, and how the effective dimensionality changes through the network. Fascinating stuff, but the paper also presents a really exciting practical application derived from this method, right? Using the detached Jacobian for steering LLMs.
Yes, this is a very compelling potential use case they demonstrate. The core idea is that since the detached Jacobian captures the specific linear transformation associated with processing a given input, it implicitly encodes the semantic concept represented by that input, at least in that specific computational context.
Right.
So they propose taking the detached Jacobian computed from an intermediate layer for a short phrase representing a specific concept, say, the phrase, the Golden Gate.
Okay, so you compute and store the Jacobian for your target concept phrase, the Golden Gate. Then what?
Then you can use this pre-computed detached Jacobian from the concept phrase as a kind of conceptual steering operator. When you process a different input phrase, maybe something totally unrelated, like here is a painting of the, you can actually apply that stored Jacobian to the intermediate activation of the new input phrase at the corresponding layer.
And applying the Golden Gate Jacobian to the painting of the input activations, what does that do?
It effectively steers the model's internal representation for that new semantic space defined by the concept Jacobian you applied. The results they show in Table 4 are quite striking.
How so?
Even with potentially awkward input combinations, the steered output becomes heavily biased towards the steering concept. So steering, here is a painting of the Golden Gate Jacobian, makes the model much more likely to generate text about, well, the Golden Gate Bridge.
Wow.
And it's potentially efficient too, because you only need to compute the steering Jacobian once for the concept you want to steer towards.
That's a very tangible demonstration. It shows how this deep academic insight into local linearity can translate directly into a potentially powerful tool for actually controlling LLM behavior at a semantic level.
Very cool. Okay, so we've covered the innovation, the method, the validation, the insights, and an application. What about the downsides? What are the limitations of this detached Jacobian approach?
The paper is actually very clear about this, which is good academic practice. The key limitation is that the numerical exactness of this linear representation holds only at the specific operating point at which the matrices were computed.
Meaning only for that exact input sequence used to calculate it.
Precisely. Even a tiny change or perturbation to the input embedding, which would correspond to using different input words, or even just slightly different numerical representations of the same words, would result in a completely different detached Jacobian.
Why is that? It goes back to the global picture. Globally, the LLM's internal function is highly nonlinear. You can think of the underlying mathematical manifold it operates on as being highly curved. A linear approximation, even an exact one like this at a point, is only accurate at that single point. The slope, or the linear behavior, changes rapidly as you move even slightly away from that point.
So it gives you a perfect instantaneous snapshot of the computation for that specific input, but you absolutely cannot assume that same Jacobian applies even to a very, very similar input.
Exactly. It's a local snapshot, not a general rule for the neighborhood. The paper does note this might be slightly less problematic for LLMs because they typically operate on discrete tokens selected from the vocabulary rather than continuously wandering through the embedding space. But it's still a fundamental boundary condition on how far this specific linear representation can generalize beyond the exact point it was computed for.
Caveat. So to wrap things up then, this research seems like a really significant academic contribution. It identifies and empirically validates nearly exact local linearity in these big open weight LLMs just for a given input sequence.
And it provides a genuinely novel, powerful technical method, the detached Jacobian, to reveal and then leverage this property. It really does open up entirely new avenues for local interpretability, using all those well-established tools from linear algebra.
For you, the listener, hopefully this deep dive helps cut through some of that black box mystery. It shows one cutting edge technical approach researchers are developing not just to see what LLMs do, but to actually start understanding how they do it, at least locally, for specific inputs.
It feels like a foundational piece of work, really. It complements other interpretability efforts and definitely hints at exciting future research directions, maybe using this animal safety or understand the origins of bias and toxicity by examining these local linear transformations in specific contexts.
Yeah. This whole deep dive into local linearity and the detached Jacobian, it really leaves you with something to ponder, doesn't it?
Hmm.
If for any specific sequence of words you feed it, you can accurately model the incredible complex calculation of a large language model as essentially a simple linear system. What does that fundamental property tell us about the underlying structure of the data these models learn from, and maybe even about the very nature of the computations they perform to understand and generate something as complex as human language?